Okay, so example 5. Find the critical values for f of x equaling root x. So we're going to again find f prime of x, step 1. Step 2, set the derivative equal to 0, and then 3, solve. All right, no big deal. We've done this 4 times already. We're pros. So remember, this is also x to the 1/2. So we know that the derivative is 1/2 x to the negative 1/2, or 1/2 root x. So what do we do here, right? That's the question. Well, f prime of x does not exist at x equaling 0, right? So that was the second part of our definition of critical values. Right? It also tells us where the derivative doesn't exist. We don't exist because if I set this equal to 0, well, then we would be the only number that would get us even not even, I don't want to say close, but we can't have 0 in the denominator, right? We cannot divide by 0. So in this case, we don't exist at that location. So again, just pointing out that we sometimes don't always have local extrema at locations of critical values. Because if I set this equal to 0, 0 equals 1/2 root x, even if I multiply the 2 over, then that's still 0 equals 1/root x. And again, that would be undefined. Poo-poo. Okay, so now the official definition of relative extrema. A critical value is also a point on F for relative extrema. Max and mins have slope of 0. Thus, f prime of c equals 0 is a potential location of a max or min. Okay, let's see. Yeah, I lost my place in my definition. We have a max if f prime of c on the left is positive, okay, meaning going up, and f prime of c, oops, excuse me, is less than 0, meaning going down. So we form this like mountain type thing, right? And a min, that should be on the right as well. If f prime of c on the left is less than 0, again, so here you'll have this, the downslope, upslope for the min. And f prime of c on the right is greater than 0. So that's why the sign chart is important. It helps us find where are the hills, where are the valleys. Okay, so 6. Show that f of x equaling x cubed has a critical value, but no extrema. So I would really like for you to pause, give us a whirl, and then press play when you are done. Okay, we're back. So same old, same old. So we're going to find the derivative, the 3x squared. We're going to set it equal to 0. Okay, so that says that x equals 0. So now we have our sign chart. Our only number of interest is 0. So I've got x, f prime of x, and then f of x. So if I choose, say, -10, again, you can choose -1, it doesn't matter. That is a positive number. So f is increasing, right? Because that slope, that says positive slope. So we're increasing. Also note that the arrow you draw is something with positive slope. Then if I choose 10, again, that's 300, also positive. So positive slope. So notice that there's no sign change, right? No sign change. So sad. No sign change, so it's no critical value. If you're curious, it's because if we draw it like this, it kind of, if I could draw better, it kind of levels off. It doesn't quite level off, but we're just always increasing from negative infinity to positive infinity. So while just by the definition of what we do, it looks like we have a potential local extrema, we actually don't, right? So again, that's why critical values are potential, not always a local extrema. All right, so 7, really and seriously pause the video, give it a whirl, and then press play when you're ready. Okay, so we're gonna take the derivative, 3x squared minus 18x plus 24, because remember the derivative of a number, of a constant, is 0. We're gonna set it equal to 0, 3x squared minus 18x plus 24, 3, negative 18, 24. All are multiples of 3, so to make our lives easier, we're going to factor out of 3. So it's x squared minus 6x plus 8. So now in factoring, we've got x and x. Two numbers that multiply to 8 yet add to 6 are 4 and 2, negative and negative. So taking each term, setting them equal to 0 and solving. Right here, we get that x equals 2. Here, we get that x equals 4. Now going to do the sign chart. Remember, this is a number line. We want 2, 4 in numerical order. Here's x, f prime of x, f of x. A test value, again, like I said, if 0 is there, I'm going to use it. So I can plug in 0 into any version of this, and we're good, right? Again, we're plugging 0 into the derivative because this is called the first derivative test. Also think of it as you're just working your way up. So you're just plugging in your test value into this cell here, working up. So that gives us a positive number, right? Because if we get rid of those two terms, we're just left with positive 24. So f is increasing. Then let's say I use 1. Well, then that's going to be a negative times a negative, which does give us, oh, excuse me, not 1. Hello, what am I talking about? See, this is why I hate making these videos. My crazy brain, I need you to here to yell at me. I tried to use 1, silly lady. The number between 2 and 4 is 3. There we go. So this is a positive, right? 1 times a negative, negative 1, which gives us a negative. So we're decreasing. And then again, let's say we use 10, my favorite Goldilocks kind of number. Positive times a positive is positive. So f is increasing. So since we have the sign changes, we know that we have a max here and a min here. Okay, so we have a max at x equaling 2 and a min at x equaling 4. If we want the y, right? So if we want the y, we would then find f of 2, which I've done before. It's at 6. Okay, and f of 4, you just pop in f of 4 into here, which I've already done, is actually 2. Okay, so the point of the max is 2 comma 6, and the actual point for the min is 4 comma 2. Okay. I think maybe, let's see, how long has it been? I have a little timer here, so I know I don't go over time. 32 minutes. Yeah, we're one more page at least. One more page, I think. and then we'll save the drug administration for class. Okay, moves. Here we go. Actually, stop the video. We'll do another one for this one.